If carbocation rearrangements ever confused you, this video is about to change that. By the end of this video, you're going to be able to spot them and get through them super simple, super easy, so just pay attention and I'll make it super easy for you. Let's jump right into it. So let's suppose that we are doing this SN1 reaction where this iodine is the leaving group and this bromine is the nucleophile. But you notice that the bromine actually ends up on this carbon right here, and you see that it's sitting right here. So how did that happen? How did we go from the leaving group being on this carbon, but now the nucleophile ends up on this carbon? Well, this is because of a carbocation rearrangement. So the first step in an SN1 reaction is when the leaving group leaves and we form a positive charge on the carbon that had the leaving group. So the positive charge is going to sit right here, and then this positive charge is actually going to move on to this carbon. How do we know? Because that's where the bromine is going to be sitting. So how does the positive charge move over to that carbon? Well, we do a methyl shift where the methyl moves over to the carbon that originally has the positive charge. And so now the positive charge sits on this carbon, and then a bromine atom is going to come in here, and it is going to attack this carbon with the positive charge, and that's how we get our answer. So for you to understand the different types of carbocation rearrangements, you have to understand first the different types of carbocations. And a carbocation is just a carbon with a positive charge. The first type of carbocation that you should know about is something called a tertiary carbocation, and that's when you have a carbon with a positive charge, and that carbon is bonded to three other carbons like we have right here. This is called a tertiary carbocation. The next type of carbocation is when you have a carbon with a positive charge, and that carbon is bonded to two other carbons. That is called a secondary carbocation. The next type of carbocation is when you have a carbon with a positive charge, and that carbon itself is bonded to only one other carbon, and this is called a primary carbocation. And then lastly, you can have a carbon with a positive charge, and that carbon is not bonded to any other carbon. So you can see here that this carbon is not bonded to any other carbons, and this type of carbocation is called a methyl carbocation. And what you need to understand is that a methyl or a primary or a secondary carbocation are all going to try and become tertiary carbocations, or at least move up towards a tertiary carbocation. They're all going to want to try and become more stable, and that's why carbocation rearrangements occur in the first place. So now that you understand the different types of carbocations, now we can talk about the different types of carbocation rearrangements, and there are two. One is a hydride shift and the other is a methyl shift. So now we can compare and contrast hydride shifts and methyl shifts. So let's start first with a hydride shift. So suppose that we have this carbocation with this positive charge sitting on this carbon. Well, this is a secondary carbocation, but this positive charge would be a lot happier if it were to sit on this carbon, because then it would become a tertiary carbocation. So in this case, this is the destination carbon where the positive charge wants to go, and this is the original carbon, which is where the positive charge is currently sitting. And what happens during a hydride shift is that a hydrogen on the destination carbon is going to move over to the original carbon, and then the positive charge is going to move over to the destination carbon. And so if we draw out what that looks like, we're basically going to have the same exact structure, but now the positive charge is sitting on the destination carbon, and that is a tertiary carbocation, and that's more stable than this original secondary carbocation. So now let's focus on methyl shifts. So suppose that we have this positive charge right here sitting on this carbon, and this is a secondary carbocation, but this positive charge would be a lot happier on this carbon because this carbon is bonded to all these other carbons, and that would make it a lot more stable. So in this case, this is the destination carbon and this is the original carbon with the positive charge. So what happens during a methyl shift is that a methyl group from the destination carbon is going to move over to the original carbon, and then the positive charge is going to shift over to the destination carbon. So now if we draw out what this would look like, well, basically we are going to have a very similar structure, but now this destination carbon has only one methyl group and the original carbon has a new methyl group, but the positive charge has moved over to the destination carbon, and now we have a tertiary carbocation as opposed to the original secondary carbocation. So now that you understand the differences between a hydride shift and a methyl shift, we can learn about how to decide when to use a hydride shift or a methyl shift. And to get this right every single time, you can just remember this rule that I have on the screen for you. If the destination carbon has no hydrogens to shift, then you will always do a methyl shift. But if the destination carbon does have hydrogens to shift, then you will always do a hydride shift. So for example, let's say that we have this carbocation with a primary carbon right here. So this is a primary carbocation, but this positive charge would be a lot happier on this carbon because then it would become a tertiary carbocation. So in this case, this is the destination carbon and this is the original carbon. And here we can see that the destination carbon has a hydrogen. So according to our rule, we are going to do a hydride shift. So the hydrogen is going to shift towards the original carbon, and this positive charge is going to shift towards the destination carbon. And so if we draw out what we would get after this hydride shift, we're basically going to have the same exact structure, but now the positive charge is sitting on this tertiary carbon. All right, let's try another example. Here we have a primary carbocation, but it would be a lot happier on this carbon with all of these other carbons that it is bonded to. So therefore, this is the destination carbon and this is the original carbon here. And in this case, our destination carbon does not have any hydrogens for us to shift. So in this case, we are going to do a methyl shift. So we are going to shift one of the methyls over to the original carbon, and the positive charge is going to move over to the destination carbon. So if we draw out what we would get as a result of this, we are going to have our original ring right here. And then now this destination carbon has one less methyl, and the original carbon has one extra methyl group right there. And remember, the destination carbon gains the positive charge. And this is the product of this carbocation rearrangement here. All right, that's how you do carbocation rearrangements. If you want more of my videos for free for all chapters in Orgo, click the link in the description. It's completely free. You don't need a credit card. Just try it out by clicking the link in the description. I hope you learned, and thanks for watching.